All right, pre-calculus folks, this will be the last video for the section on the law of cosines. What I want to do is tell you about an interesting application of the law of cosines. This is related to like piston engines, steam engines, that kind of thing. There's a mechanism inside a piston engine, which is called a reciprocal engine, that is called a slider crank. And let's open up this image here. So this is a picture of like how an engine works. What's going on is you've got something either like a combustion, right? So some sort of explosion, or maybe like compressed steam or something like that, which is powering a piston. And so you've got steam pushing on it and then being released, or an explosion pushing it and then it comes back. Something is causing this to bounce back and forth over here. And then what that does is it moves this back and forth, and there's this bar. This is going really fast, so it's kind of hard to see, but I'll show you a few other pictures. There's a bar right here that connects this piston action, this linear motion back and forth. It connects that to a wheel, and it translates that into circular motion. Okay, and the way that the linear motion and the circular motion are related to each other actually involves the law of cosines. So I'm going to show you just a couple other GIFs here. Yes, I say GIF, fight me. There's a couple other GIFs here that just kind of demonstrate this idea in a little simpler fashion. So here's the piston going back and forth, and here you can see there is a bar of a fixed length connected to connected to like a wheel of a fixed radius, and these parts are there's hinges here, and this is allowed to spin around. So there's a point here going around in a circle, and then that's connected, and there's a hinge on the piston here, which allows the back and forth motion to be translated into circular motion. Here's another picture, piston going back and forth. There's the wheel going around there, and one more. Here you even see it with vectors displaying the velocities of these two things. And you see this one is going slow then fast and slow then fast, going back and forth. So, all right, so what I want to do is come over here to my sketchbook. I'm going to draw you a picture of this. Oh, where's my notes? I'm going to draw you a picture of this, and then we're going to label some things, and we're going to try to figure out what the heck is going on with this situation. So what we have is we've got the piston going on over here. Okay, so we have some sort of a shaft in which you have something going back and forth. So this thing is going to be going kind of back and forth there and there. And that back and forth motion there is what we're interested in. What we want here is to now connect that to the wheel. So I'm going to put a line like this that connects to the center of the wheel. So this is not necessarily an actual connection here, but that distance between the center of the wheel and this point is what we're going to use to measure the motion of this, the back and forth motion over here. The center of the wheel is a fixed point, so we can measure the location of this point from by how far away it is from the center. That distance there I'm going to call x. That's going to be a variable. But then the way these are connected to each other is that there's a bar that connects. Well, sorry. First of all, there's a fixed radius here. The fixed radius of this wheel radius, we're going to call it r, and we're going to take a point which is on the wheel, and that point is going around. Okay, so that's like wrapping around. And then these are connected to each other with a bar of a fixed length as well. So that length we're going to call L. All right, so we have L and R, which are constants. So L and R are constants. Okay, X is variable. And the other variable we have here is this angle, theta. Theta is variable. Now let's say that what we want, this, by the way, this piston engine, this slider crank here, could be in like steam engine, like in a train. Like maybe this is the train wheel going around, and here's the steam end, this the piston as part of the steam engine, which is moving back and forth here, driving the train wheel. What we want is we want this wheel to rotate at a constant angular speed. Or maybe you want it to be variable, but we at least want if the object like the train is traveling at a constant speed, then we want this to be rotating at a constant angle. So let's assume that that's happening for the sake of this problem. Let's assume constant angular speed omega. So remember omega. Omega is omega is the angle that it passes that we pass through divided by the amount of time. Okay, so theta divided by time t, which would be another variable. So that's omega. We learned that back at the beginning of our trigonometry unit when we first learned about angles in general. So let's say that constant omega is 1/2 of a revolution per second. That's a pretty accurate. I got that from looking at this. I figured this goes around about 1/2 a revolution every second. So I thought, okay, let's use that. That looks pretty good. So that it would be, by the way, in radians, that's going to be pi radians per second, because pi is 1/2 a revolution. So then theta over t is going to be pi, all right? So that means theta, by the way, is going to be pi times t. So theta this angle as a function of time is pi t. We're going to need that later. Okay, so file that away. We'll come back to that. So now, based on this graph, what we have here is an oblique triangle, relationship here between these three sides. Okay, and no matter where the bar lines up on the wheel, it's going to be an oblique triangle, whether it's going to be over here or whether it's going to be like over there or whether it's down there. It doesn't matter. All of these are oblique triangles. So the relationship between the sides and the angle are going to be given by the law of cosines. Well, I know we should use the law of cosines because we have three sides and one angle, and that's what the law of cosines is to do. Relate those things to one another. So I am going to do this. I'm going to take the side opposite the angle, which is L, and L squared is going to be the sum of the squares of the other two. So like r squared plus x squared, and then minus 2 times r times x. So 2 times each of those, and then times the cosine of the angle theta. Now this gives me this law of cosines right here. Basically, just gives me a relationship between x and theta. Right? So if we're interested in how the linear motion x is related to the angular motion theta, the law of cosines is the thing that relates them to one another. And so let's put in some specific values. Let's specify, let's say L is 10 inches and R is 4 inches. Okay, so there's, and I got that as well by sort of looking at this diagram, this example, and kind of eyeballing the rough distances. I said, okay, if this bar connecting the piston and the circle is of length 10, then what would the radius be? It looks like it might be about 4. Okay, so that's what I used, 10 and 4, and then we're going to use theta equals p because we want theta to be changing at a constant rate. So that's our 1/2 a revolution per second. So now putting in all that information, we get 10 squared equals 4 squared plus x squared. X is still variable. Okay, x is still our variable. Minus 2 times 4 times x times the cosine of pi t. All right, let's simplify this up a little bit. 100 equals 16 plus x squared minus 8x cosine of pi t. All right, so now we're going to graph this. Let's go back to Desmos and graph this. In order to graph it, we're going to use t equals y because we've got to have, I want to go ahead and have x be x, so I'm going to use x on the x-axis, but we've got to have something on the y-axis, so I'm going to use the time on the y-axis. So what we're going to get here, let me just give myself a little more space. What we're going to get is a graph that looks like this, where we have time going that way, and then this is x. So we're going to be able to, like, you could visualize the x distance bouncing back and forth as time increases, going up. So let's go graph that. I'm just going to look at it and remember what it is. Okay, I think I can do that. Here's my graph. So we have 100 equals 16 plus x squared minus 8 cosine of pi times y. That was going to be, that would have been t, but we're using y. That doesn't look quite right, so I'm just going to double check that I didn't miss something. 16 plus x squared minus 8. Oh, 8 minus 8 times cosine. I think I missed the 8x. So let's go back and grab that. 8x. Yeah, there we go. There's an x there. There we go. All right. So by the way, the graph also has some stuff going on the left side, but we can ignore that because those are the negative values. We don't really care about that. We care about what's going on over here. The x, the distance between the circle and the piston is bouncing back and forth. So we can visualize this as like the motion of the piston bouncing back and forth as time increases. Time is going up in the vertical direction here. So we see this is the function. It's not exactly a straight up sine or cosine wave. So it's not really a sinusoidal function. It is related. It's similar. It certainly has a similar shape, but it's not exactly sinusoidal. It has this, this sort of bouncing back and forth type of behavior, but it's a little bit more complicated, the equation. Now, technically, you could solve this for x, but solving this for x would require the quadratic formula because of the fact that you have an x squared term, an x term, and then a constant term. So I'm not going to go ahead and do that. I'm gonna leave it in this what's called an implicit form where it's not actually solved for the output variable. I want to leave it implicit, but I think the graph kind of speaks for itself here. And now that I have this relationship, what you could do in calculus is you could take this relationship and do something called implicit differentiation, where you go ahead and figure out what the rate of change is, and you can find the rate of change in x with respect to time by doing something like that. This is the type of thing you might do in, the subject in calculus you'll encounter later that's related to this. Sorry, oops, is called related rates. Because we're looking for the relationship between the angular speed of the wheel, and let me put this on the screen again. We're looking for the relationship between the angular speed of the wheel and the linear speed of the piston as it bounces back and forth. So there we go. That's the example.